Hello, this is episode 4, Array Operations. In the previous episode we talked about arrays or matrices, and now we're going to talk about some of the operations you can do on matrices. These include matrix multiplication, element by element multiplication, raising a matrix to a power, raising each element of a matrix to a power, inverting a square matrix, element by element division of matrix elements, computing the determinant, and computing eigenvalues of a matrix. If you don't know what those things are, that's fine. Some people will use them. You'll maybe learn how to use them later on. First is we're going to talk about multiplication by a matrix. Okay, the first thing you can do is multiply a scalar and a matrix. So just a number times a matrix. When you multiply a number by a matrix, you basically multiply every element of that matrix by a number, by that number. And here are some examples. So we'll just do a quick demo to show how that works. So this is a 2 by 3 matrix. So if we do 2 times A, it multiplies every element by 2. Simple enough. That's how that works. So why might you do this? Well, if you have a matrix that talks about a set of distance in feet, you can convert it into array with meters by multiplying the whole matrix by, in this example, 12 to get turned to inches, and then times 0.0254, which is the number of meters per inch times that vector. Another thing you might do is if you have, say, an array of frequencies in, let's say, kilohertz, and you wanted to convert it to hertz, you can take the whole array and multiply it by 1,000. Again, you can scale things, like if you double everything, you can just do it with one vector operation. The next thing you can do is multiplication of 2 vectors. Now there's 2 ways to do that. So one of them's so the general rule is you multiply the first row of the first matrix by the first column, add them up, and that being the first row of the first column of the result. You keep doing that with each row and each column until you've multiplied them all. So for instance, so we're going to get given 2 matrices A and B, you can compute A times B. So there's a general rule, it's written there, but it may be better to show a little demo first. So we have, let's say we have, let's clear all to get rid of all the variables. Let's say A equals 1, 2, 3. And B equals, make that a column vector. What's A times B? Well, the way that works is you multiply the first row 5 times the first column, and that gives you the first result of that matrix. But you can also do it the other way. What's B times A? That's a square matrix. So you start out with a column vector, you multiply the first row times the first column, and you can work it out. So the matrix multiplication is not commutative, order is important. And they're not even the same type of answer. Notice A times B is a number, a scalar, a 1 by 1 matrix. B times A is a 3 by 3 matrix in this example. So the order that you multiply the matrices in makes a difference in what the output is. This also, if you multiply a row vector times a column vector, that's also known as taking the dot product, which gives you a number, a single number. The other thing where you multiply it the other way around is called the outer product, and it gives you a matrix. So again, you start with the first row of the first matrix by the first column and add them up. That's the first one, and then you keep going, multiply the first row by each column and add them up to generate the first row in the column. and then you just continue doing that. That's how MATLAB does it automatically for you. You may have learned this in high school algebra, how to multiply matrices. So here's an example just like the one I gave. This is a example where you do the outer product, where you do multiply them in the opposite order. Again, you multiply this first row here, I don't know if you can see that, first row by the first column, and you get 4 times 1. And then you do the first row times the second column, and you get 4 times 2. First row times the third column, you get 4 times 3. And you continue throughout the matrix. This row times this column gives you this number, and eventually you end up with this square matrix for these particular vectors. But the size is important also. For this product to work, both have to have the same number of elements. So to multiply 2 matrices, the first matrix has to have the same number of columns as the second matrix has rows. That's the basic rule. As long as that's the case, you can multiply 2 matrices and there's no problem. And I'll give you an example of what can go wrong. So if you have, let's say A equals, let's make it a square matrix. And let's say B is like a 3 element vector. Whoops. A times B is not going to be defined. Go error. So you can't multiply those. You can only multiply things following the rules where the number of columns in the first matrix is equal to the number of rows in the second matrix. So matrix multiplication is only defined for matrices of appropriate size. Okay, now we're going to move on to multiplication of a matrix by a vector, which follows the same rules. Again, you take the first row, multiply it by the first column, and you get this thing. You add them together. You multiply this row by this column and add them together. This is not defined, again, because the rules for multiplications are not correct. So even though if this was matrix A and this was times matrix B, A times B is defined, but B times A is not defined. So it may be the case that one multiplication is defined and the other is not. You can multiply a row vector times a matrix of the appropriate number of appropriate size, but this is not defined. I basically did that demo. You can also multiply 2 matrices together. And even if you can multiply, even if A and B can be multiplied in both orders, you will generally not get the same answer. So here's an example. Let's do something like that in a demo. Let's do A equals, let's see, 1, 2, 3, 4, 5, 6, and let B be a 2 by 3. Sorry, a 3 by 2. Now you can compute A times B, and you get an answer. You can also compute B times A, and you get a completely different answer. In fact, it's a different type of matrix. So obviously, matrix multiplication does not commute. If you change the order, you might even get a different type of object, and you might even get, even if it's the same size. So you can do a square matrix. Let's do a square matrix, which you can define, which gives you something the same size when you multiply it. Let's see. Whoops. let's say B equals something else, 2, 3. Just to get some random matrix in here. Whoops. What did I do wrong? Oh, need a comma there. So we can do A times B. You get one answer. And you can do B times A. You get a completely different answer. So matrix multiplication does not commute. It might not necessarily even give you the same size matrix. So, but if you know the basic rules, if you can figure this out, it's important to know that order is important in the matrix operations. So you can raise a matrix to a power, and that's basically multiplying a matrix by itself, however at many number of times. So like for this to work, a matrix has to be square. Okay, raising a matrix to a power. You can raise a matrix to a power by multiplying itself that number of times. For instance, the matrix A squared is A times A cubed is A times A times A. In this special case, A has to be square. It has to be a square matrix, the only way you can multiply it by itself. A special case is -1. A to the -1 returns the inverse of matrix A, which may not exist. An inverse of a matrix A is a matrix that if you multiply it by its inverse, you get the identity matrix, which is a matrix which is 1 on the diagonals and 0 everywhere else. There's more to this. You can raise matrix to a fractional power. You can raise a matrix to a matrix power, but that's not something we're going to cover here, and you probably won't be doing that unless you're doing some esoteric computation. So let's go over that in a demo. Okay, we're going to do a demo. We're going to have this matrix B. We just created it out of randomly. We can do B squared. Gives you something. You can do B cubed. You can do B to the -1. Now if you take B times B to the -1, you basically get something with 1s on the diagonal, and these other numbers are very close to 0. This is just some errors in the computation. So this is not a very good matrix to do this with, but there are worse choices. So yeah, that's the other thing you can do. You can also do element-wise multiplication of two matrices. Whenever you put a dot in front of it, an operator, that means to do it element by element. So if you do a dot times, that means every element in A, or if you had a matrix A and a matrix B, if you have every element in A, you multiply it by a corresponding element in B, and you put that in that location. So element-wise multiplication can only be done with two arrays that are the same size. You can also do it to the other operators. Dot slash divides the elements of two arrays. Dot plus adds the elements, but that's actually no difference than plus, and same with dot minus. Dot caret gives takes every element and raises it to the power. So let's look at that. Okay, let's start, say, with the matrix B again we have here. Let's take B dot times B. That multiplies each element by itself, which is actually the same thing as taking B dot caret squared. Gives you the same matrix. So you can do, I created another matrix here like that. We can do A dot times B. That gives you a different matrix. You can do A dot divide B. That divides each element wise You can see you divide 1 by 2 and get a half. You divide 2 by 3 and you get 2/3 basically, or 1/3. Yeah, or wait a minute, 2 by 6. You get 1, and that's it just keeps doing that. Okay. So you can also do A plus B, which really is the same as A dot plus B. Oh, okay. So this version apparently doesn't do that anymore, but Matlab still does that. Okay, the next topic is the determinant. Now we're just going to assume you know what a determinant is. It's basically a number that characterizes a matrix. And a matrix has an inverse only if and only if its determinant is not 0. If a matrix has a determinant of 0, it's uninvertible. It has no inverse. So some examples here are, this is a determinant of a 2 by 2 matrix. It's written out in math with something that looks like absolute value signs. And this is the formula for a 2 by 2 matrix. A 3 by 3 matrix goes by this formula here. There are a set of rules you learn when you do that. We're not going to go over the mathematical rules. Like I say, we're assuming that you know what that is if you're going to be using a determinant. So we're just going to show you how you compute the determinant of a matrix in Matlab. Okay, let's say we already have this matrix here. Let's say A. We can just do det A. Gives you the determinant. So this is a very bad matrix. I mean, its determinant's near 0. So you might have trouble inverting it. Might not have an inverse. It probably doesn't. So if you do A times A inverse, that that doesn't look anything like the identity matrix. That's because the determinant was close to 0. So this numerically it doesn't even make sense to do that operation. Now B, if you did this other matrix we looked at before, B, if you looked at the determinant of B, it's a reasonable number. So B times B inverse looks more like the identity matrix. So that's how you can determine the determinant. It's just det. It is useful if you have to do an matrix inverse to check and see. There's another way to do that, but we'll get into that in a more advanced course. But one way to check is if the determinant is near 0, you're not going to get a good inverse for the matrix. Okay, the next topic is eigenvalues. So what an eigenvalue is, if you have a matrix A and there are special vectors B and scalars lambda such that AB equals lambda B, in other words, this matrix multiplication, it basically just scales the vector. For these solutions, the certain vectors and scalars that satisfy this equation, the scalar is called the eigenvalue and the vector is called the eigenvector. So rewriting that equation, you write the matrix equation A minus lambda B equals 0. Now this equation has the trivial solution B equals 0, but we're not interested in that. We're only interested in non-trivial solutions, which is B not equal to 0. And that only occurs if this matrix is not invertible. The A minus lambda is not invertible. So if this determinant of A minus lambda equals 0, it's called the characteristic equation. Once you solve for the lambdas, that gives you the eigenvalues and the eigenvectors. In this course, we won't go why it's over important, but we'll show how you make it work in Matlab. I'm going to go over one more thing that's helpful in Matlab and Scilab. You can type, if you want help on a function, one of the ways you can do that is just you can type help and the function name, which in this case is going to be eig, and it will print out in here what eig does for you. So if you get a matrix and you want the eigenvalue, this tells you the syntax. If you want the eigenvalue, you just say eig. If you want the eigenvectors and the eigenvectors and eigenvalues, you use this syntax. Okay, so given our matrix before, let's say B, let's say I of B. That gives you the eigenvalues of the matrix B. Now let's do this other form, V comma B, so this is sort of a matrix, equals eigenvalue, eig of B. So this gives you, the eigenvectors are the 3 columns there, and the eigenvalues are the diagonal of this matrix. The other thing that might be helpful if you want a more better formatted help, in all of these you type doc eig, and it gives you it brings up an editor with some sort of thing that gives you a better formatted version of the help for this function. This works both, I don't know about Scilab, but it does work for Octave and it works for Matlab. So it just gives you a better formatted help on the function. So now we're getting into more complicated functions. Now notice this particular function does something interesting. It returns more than one thing. So this is basically how many functions return more than one thing. And by default, without this, you only get one thing. So eig by itself just gives you the eigenvalues. Eig with this sort of thing on the left-hand side gives you 2 things, the eigenvectors and the eigenvalues. Now we're going to start seeing some functions as we go on in this course where a function like this will return multiple things. And this is the syntax you use to get those things. Okay, so here we're just going to give you an exercise to try some of these things out. Just create a row vector with 3 elements and a column element. It could be any element you want. Compute all these things. Compute a 3x3 matrix. Compute all these things. Compute the determinant and compute the eigenvalues and eigenvectors. And that'll be it for this module. All right, we'll see you next time.